So far in this course, we have worked extensively with arithmetic computation, with logic expressions, etc. But one thing that has been constraining us is that so far we have only dealt with integers. We do not know yet from the lectures that we had how to handle real numbers. And lots of computing happens with real numbers. There are lots of, any computer that interacts with the physical world is likely to be using real numbers. Computing simulations in chemistry, in finances, in a number of other areas will use real numbers. So our learning and our education in computer architecture is not complete until we are able to handle real numbers. So let's start with something that we already know. Let's recall how we do normalization when we have numbers in base 10. So let's say that I have the number 26.73 in base 10. I know that this is 2 times 10 to the 1 plus 6 times 10 to the 0 plus 7 times 10 to the minus 1 plus 3 times 10 to the minus 2. And I can represent this number as 20 plus 6 plus 7 over 10 plus 3 over 100. If I normalize this number, so this number as expressed is not normalized because the decimal period is not to the right of the first non-zero digit. So if I want to normalize the number, what I need to do is to move the decimal period so that it is after the first non-zero digit of the number, and then I have to indicate how many positions I need to move to denormalize later. So I need, in this case, I move the decimal period 1 position to the left. Therefore, I have to multiply this by 10 to the 1. In base 2, we do something very similar. If I have the number 8.25 in base 10, this number is 2 to the 3 plus 1 over 4, because 0.25 is 1 divided by 4. So I can express this number as 2 to the 3 plus 1 over 2 to the 2, which is 2 to the 3 plus 2 to the minus 2. Now, if I express this number in binary, this will be the number 1000 binary period. Remember, this is not the decimal period, it's the binary period, 01. And I use the 2 here to indicate that this number is in base 2. Sorry, let me move this picture up there. So this is to indicate that this is the number, the base 2. So this number is also not normalized because the binary period is not to the right of the first digit that is not 0. So to normalize this number, I'm going to have to move the binary period 1, 2, 3 positions to the left. As I move the binary period to the left, I need to multiply by the base denotation to the power of the number of positions that I move. The similar way that I move in the 26.72, I move the decimal period 1 position to the left, and I multiply by 10 to the 1. In the binary representation, I move the binary period 3 positions to the left, and I multiply by 2 to the 3. So this is the normalized representation of 8.25 base 10 when expressed in base 2. So let's do some decimal to binary conversion and some normalization. So if I give you the number 581 decimal 21875 in base 10, and I ask what is the binary representation for this number. First, we need to find what is the binary representation for 581, and we can use the method of the repeated division. So I divided 581 by 2, I get 290 and the remainder is 1. Then I got 145 and 0, 72 and 1. So I repeatedly dividing the number by 2 and make a note of the remainder. 36 by 2 is 18 with 0, 18 by 2 is 9 with 0, 9 by 2 is 4 with 1, 4 by 2 is 2 with 0, and 2 by 2 is 1 with 0, and 1 by 2 is 0 with 1. And now I read the number from the bottom to the top here. So 581 is 100,100,101. Now, how do I convert the fraction that I have here into its binary representation? What I'm going to do is multiply the fraction by 2. So when I multiply the fraction by 2, I get 0.4375. And now I will keep multiplying. I get 0.875. I multiply again, I get 175. But notice that now that I got 175, when I go do the multiplication, I throw away that 1 and I just multiply the fraction. Is 0.75 by 2 is 1.5, and then 0.5 by 2 is 1. And this is the method of the repeated multiplication. And this is the number that I need to represent, and in this case I read from the top down. This is my most significant digit, the digit closest to the binary period. This is my least significant digit, the digit that's far away from the binary period. So the fraction 21875 is actually the binary fraction 00111. So this is the binary representation for 581. Of course, it's not normalized. If I wanted to normalize, I have to move 3, 6, 9 positions. So if I move the binary period here, I will have to multiply by 2 to the 9. Now let's talk about how we can represent those real numbers in a representation that we call the floating point representation. The representation for non-integer numbers may include very small and very large numbers. It's similar to scientific notation. In scientific notation, I could have minus 2.34 times 10 to the 56. I could have plus 0.002 times 10 to the minus 4, or plus 987 decimal period 02 times 10 to the 9. In binary, I have something similar. The number can be plus or minus, and then I have 1, and then the binary period, and then the fraction, that's called also the mantissa of the number, in base 2 times 2 to an exponent. This is the type that's used for example, floats and double in C. So the first, in scientific notation, the first number is normalized, but the 2 numbers below are not normalized. So there is a standard for floating point representation that's defined by the Institute of Electric and Electronics Engineering, and this standard is the standard 754 from 1985. And the reason this standard was created is because there were divergent representations. So different computer manufacturers and different software people were using different representations for real numbers, and that caused lots of problems, as you can imagine, when you try to do transactions between different systems. And there was also a portability issue for scientific code. Now, this standard is almost universally adopted, so this is the standard to use. And there are 2 representations in this standard. There is the single precision representation that occupies a real number occupies 32 bits, and there is a double precision representation where a real number occupies 64 bits. So this floating point representation, this IEEE standard representation will use 1 bit for the sign. That bit indicates whether the number is positive or negative and has no effect on the value of the number of the module of the number at all. So I have 1 bit for the sign. Then this representation uses 8 bits for the range, that is the exponent field. So, and we call this the biased exponent because this is not the actual exponent of the number. This exponent uses a biased representation. And we're going to see in a minute what this biased representation is. The most significant bit of the biased exponent is on the left, and the least significant bit is on the right. And then the 23 remainder bits are using for the precision, or what we also call as the mantissa or the fraction field. So the fraction uses 23 bits, and again the most significant bit of the fraction is on the left, and the least significant bit of the fraction is on the right. So how I obtain the value of a number with this representation? If the bias exponent is between 1 and 254, then the number is given as minus 1 to the s, where s is the sign bit. So the sign bit can be either 0 or 1. So minus 1 to the 0 is 1, and minus 1 to the 1 is minus 1. So if the number is negative, the sign bit needs to be 1, times 1 binary period fraction. So you simply write the fraction next to that 1, times 2 to the bias exponent minus 127. If the bias exponent is 0, then the expression to compute the value of the number is different, is minus 1 to the sign times 0 dot fraction times 2 to the minus 126. So remember, the bias exponent is 0. If I use the 0 in the bias exponent over here, this would be 0 minus 127. So I have the 1 there and 2 to the minus 127. I cannot do that. If the bias exponent is 0, I must use this expression in the bottom here. So that's the way I compute my number. So let's look at one example. How is the number minus 6 and 5/8 represented in this floating point notation? So first of all, I will do a bit of manipulation with my number so that I can express it more easily in binary. So first I'm going to represent 6 as 4 plus 2. I'm representing the number in powers of 2. And I will represent 5/8 as 4/8 plus 1/8, because I also want to represent as powers of 2. And then I'm going to simplify 4/8 as 1/2. So once I have done that, I can now express this number as powers of 2. This would be 1 times 2 to the 2, plus 1 times 2 to the 1, plus 0 times 2 to the 0. I do not have a 1 there. Plus 1 times 2 to the minus 2, plus 0 times 2 to, 1 times 2 to the minus 1, that's the 1/2. I don't have 1/4 here, so it's 0 times 2 to the minus 2, plus 1 times 2 to the minus 3. So if I express this in binary now, this will be 1, 1, 0. Those are the numbers before the binary period, and then it will be 1, 0, 1, which are the numbers after the binary period. So if I normalize this number now, I'm going to have to move my binary point to the left by 2. So I have to multiply this number, the normalized number, by 2 to the 2 to maintain the same value. Therefore, the bias exponent is given by bias exponent minus 127 is equal to 2. This is the exponent that I have. So the value of the bias exponent has to be 129. So now I have to represent 129 in this bias exponent field here. This is, of course, is 128 plus 1. And remember, 2 to the 5 is 32, 2 to the 6 is 64, 2 to the 7 is 128. So I need to have the bit correspond to 7 equal 1 and the bit correspond to 0 equal 1. So this is my number, this is my bit 0 equal 1, this is my bit 7 equal 1. That value here is the value 129. My number is negative. And my mantissa is expressed here. My mantissa is the 10101, followed by all zeros to the end. So this is how, given a decimal number, I can compute the binary representation for the number. Now, if I what is the decimal value of the following floating point number? So here I give him the binary representation for a floating point number now, and I need to find what's the value. So the first thing that I need to do is to break the 32 bits into the corresponding fields for the number. So I start by stating that this is the bias exponent. So the bias exponent is 2 to the 7 minus 2 to the 3 plus 3. So how did I get that? Look, I have 4 ones here. So I'm gonna say this value here is 2 to the 7 minus the value of this bit here, that's 2 to the 3, plus here I have 1 and 2, so plus 3. So using that knowledge that those 4 ones can be represented by 2 to the 7 minus 2 to the 3, this will be 128 minus 8 plus 3, which is 120 plus 3, 123. So the bias exponent is 123 in this number, and so I need to now compute the value of the number. My mantissa is 0, so and my sign is 0, so I have minus 1 to the 0 plus 1.0 because that's the value of the mantissa times 2 to the 123 minus 127. I simply apply the values that I found from the number into the expression on the top because I have found that the bias exponent is not 0. So that gives me 1.0 times 2 to the minus 4, which is 1 over 16. So this is the value 1 divided by 16 is given by this binary representation over here. A number of years ago, actually 6 years ago, Dylan Ashley, who was a student in 229 at the time, Dylan has just finished his master's degree in artificial intelligence at the University of Alberta and has accepted a PhD in Switzerland and is moving over there, has moved over there this fall. So he's in Europe now, but he was a student in 229 and he also was one of the students that work on those summer projects where we work with the spec benchmark. And Dylan was very insistent in a question. He said, why does the IEEE standard use the bias format for the exponent instead of a choose complement representation? And he was very insistent. He says, why make things more complex? We already know choose complement. Why do we need to learn a new representation now? And when Dylan asked that question in the class, I did not know the answer. I had never looked into why we use the bias format for the exponent. So I decided to go find the answer, and then I created these slides here because I wanted not only to tell Dylan the answer, but I wanted him to be able to find it, and I want you all to be able to find such answers when you have similar questions. So how you find the answer? First of all, you need to be familiar with a site called scholar.google, and in this case .ca, but you just search for Google Scholar. Google Scholar is a wonderful site that you can use to research any technical field in any area, actually, not only in computing science. So I went into Google Scholar and I said floating point representation. And the Google Scholar is a very nice site because it will gonna return the findings by the number of citations. So the most popular writings in that area will come on top. So, and sure enough, there was an ACM Computing Surveys, which is an excellent periodic that has lots of information about everything that you want to know in computing science over the years. So this one was published in 1991, and it was called What Every Computer Scientist Should Know About Floating Point Arithmetic. So I thought that that was a good lead. I accessed that. This is an article by David Goldberg from the Xerox Palo Alto Research Center in California. And so finding that, what you do, you download the PDF, you have access to all publications from the ACM, that's the Association for Computing Machinery association and library, and you have access to every periodic in that library through your Universal of Alberta library. All you have to do is to access the library. I believe that you may need a VPN for that, but you access the library using your your ID from the university, and you're going to gain access to the entire library. So you can then download the PDF and search the PDF for what you want to know. In this example, it was bias. And by the way, as I'm talking about ACM, I also want to tell you that there is a local chapter of the ACM that was founded this term. It started actually in August, and I am the sponsor for the chapter. So if you are interested in getting involved with the ACM, there are several students on campus that are starting a chapter for that. But anyway, back to the question of why do we use bias? So I searched for bias, and sure enough, I found the answer. The answer is that an advantage of this bias representation is that non-negative floating point numbers can be treated as integers for comparison purpose. So that is the main reason why we use the bias exponent instead of using a 2 complement. So let's illustrate this issue of comparing two numbers in floating point representation with one example. Let's say that I want to compare the number 2.5 and the number 0.25, and I want to know which one is larger. So 2.5 is 2 to the 1 plus 2 to the minus 1, which can be represented as 1, 0, binary 0.1 times 2 to the 0, which is 1 binary 0, 1 times 2 to the 1. Remember, I need to normalize the number before I get my representation. And I can do something similar to 0.25, and I will find that this is 1.0 times 2 to the minus 2. Now let's look what would happen if I had my representation with an exponent in 2 complement format. So my exponent for 2.5 is the number 1. My exponent for 0.25 is the number minus 2. So 2.5 would be represented in this way. All I'm doing here is taking the mantissa from here, or the fraction, which is 0, 1. My sign is 0, and my exponent is 1. And then if I want to represent minus 2, the value 0.25, I need to represent minus 2 in 2 complements. Minus 2 in 2 complements is 1, 1, 1, 1, 1, 1 with a 0 in the end. So 0.25 would be represented as this number here. So my mantissa is 0, my sign is 0, and my exponent is 1, 1, 1, 0. So if I try to compare and I ask which one of those two is the larger one using integer comparison, the answer will be that 0.25 is larger than 2.5, which of course is not correct. If I use a bias exponent, what I have is that the bias exponent minus 127 should be equal 1. So the bias exponent should be 128. So 2.5 will be represented by this number. This is the number 128, is 2 to the 7. And my bias exponent for the exponent minus 2, the value of my bias exponent will be 125. And if I represent now the number, I will see that this number is the number has this exponent here. And when I do the comparison now, it's clear that, so I'm going to remove just the intermediate steps and show only the representation. So those are the representations for 2.5 is 0.25. On the top, using the 2 complement, which is not what the standard does. And on the bottom, using the bias format. Now, if I do an integer comparison here, I will find that 2.5 is less than 0.25, which is incorrect. And if I do the integer comparison here, I will find that 0.25 is less than 2.5, which is correct. So that is the motivation to use the bias exponent instead of using the 2 complements representation. So for the floating point representation, here is another example what is the decimal value of the following floating point number. Again, I have to take the bias exponent. The bias exponent will be, in this case, is 2 to the 7 plus 2 to the 1 plus 2 to the 0. So 128 plus 2 plus 1, which is 131. And my fraction is 00101. So I have 00101 here. And when I do the multiplication, to find the number, I have a 2 to the 4 here because 131 minus 127 is 4. So what I have is that my number is 10010 binary 1, which is 2 to the 4 plus 2 to the 1 plus 2 to the minus 1, which is 16 plus 8 plus 1 half, and this is 18.5. Another question that we want to address is what is the largest number that can be represented in 32-bit floating point using this format specified? Well, the largest number will have the largest exponent and the largest fraction. But remember that the exponent can only be up to 254. It cannot be 255. Therefore, the largest exponent that I can have is the exponent has all ones with a 0 in the end. We're going to discuss in a minute what happens when we have then all ones. So this number, the bias exponent will be 2 to the 8 minus 2 to the 1. I'm using the similar trick that I did before, is to take the number that has only a 1 to the left of this one. This will be 2 to the 8 minus a number that has a 1 in this position. This is 2 to the 1. So this is 254. And my fraction is 1 times 2 to the minus 1, etc., up to 1 times 2 to the minus 23, because I have 23 bits here. So I can represent this fraction as, again, I take the number to the left of this, that's 2 to the 0, minus this number here, that's 2 to the 23. So my fraction is 1 minus 1 over 2 to the 23. 2 to the 23 is 2 to the 10 times 2 to the 10 times 2 to the 3. So this is 1024 times 1024 times 8. If I do this computation in my calculator, I get that this number is 0.9999809. And now that I have the actual exponent and I have the fraction, I can do my computation. I have, this is a positive number because I have the sign equals 0, times 1.9999 times 2 to the 127, which is approximately 2 to the 128. This is the largest number that I can represent in this representation. The other interesting question is, what is the smallest non-negative number that can be represented in 32-bit floating point using this representation? So now for the smallest number, we wanted to have the exponent all 0, and we wanted the fraction to be as close to 0 as possible. So this is the smallest non-zero and non-negative number. So it will gonna have a 1, only the last bit of the fraction will be 1. So this is my bias exponent is 0. So the actual exponent will be 0 minus 126. Because my exponent is 0, I need to use the lower version, or the lower part of this expression, which is minus 26. And the fraction will be 1 times 2 to the minus 23. So the number will be minus 1 to the 0 times 2 to the minus 23 times 2 to the minus 126. That's approximately 2 to the 149. So far we have talked about all the possibilities for this format, but we always have kept our bias exponent smaller than 254. But we can represent the number 255 with the 8 bits that I have here. So what happens? So I could represent numbers from 0 to 255 in that 8-bit field. So what's the value represented when the exponent is 255, when the exponent is all ones? In that case, the exponent all ones indicates that I have a special value. And this special value can be, if the fraction is 0 and the exponent is all ones, then I'm representing plus or minus infinity. If the bias exponent is 255 and the fraction is not 0, then I'm representing not a number. And not a number is a very important value, because imagine that you are doing a very long simulation that will compute a very large matrix, for example. You may have a mistake somewhere in your calculation that leads, for example, to a division by 0. So you could handle that, or to any other kind of calculation that results in an error. You can handle that by saying the result of this operation is not a number. And now you use the property that anytime that you operate with a not a number, you also get not a number. So in the next day when you come to look at your results, if the error only affected a small portion of your output, it will be indicated by all those positions that have the value not a number. So it's a very elegant way to handle errors when you have errors in your computation. And so that was our single precision floating point representation. This is the last slide of this lecture. Here we present the double precision representation. For double precision, the format specifies that I still have 1 bit for the sign. Now I have 11 bits for the exponent, and I have 52 bits for the fraction. The fraction is also called sometimes the significand. And there is a half precision representation for floating point that has 1 bit for the sign, 5 bits for the exponent, and 10 bits for the fraction. And there is a very interesting story that I can tell in our synchronous meetings about the half precision, and actually we also have available tiny precisions that are used especially for neural networks.